Section 15.7. Large integer ciphers. There are many ciphers that can be constructed using large integer multiplication. Section 15.3 describes the mult128 cipher, where the message is taken in 128-bit blocks. Each block is treated as a 128-bit integer and multiplied by a secret 128-bit integer m modulo 2 to the power 128. To get good mixing, every byte of the multiplier should be non-zero. This is still weak because the low-order n bits of each ciphertext block depend only on the low-order n bits of the plaintext and the low-order n bits of the key m. This makes the encipherment of the low-order byte a simple substitution. Performing a simple substitution before and after the multiplication does not fix this weakness. Similarly, the low-order 2 bytes undergo bigram substitution, and the low-order 3 bytes undergo trigram substitution. Mult128 is rated 3. A superfast way of fixing the low-order byte problem is to combine the high-order byte with the low-order byte, for example by using the XORs or adds combining function. That would boost the rating to 5. A better solution would be to combine the high-order 8 bytes with the low-order 8 bytes using XORs or adds. That boosts the rating to 7. Here's an example. One way to strengthen the cipher would be to permute the 16 bytes. However, with sufficient ciphertext, Emily could detect which byte position has the least variability, and therefore must be the permuted low-order byte. Permuted mult128 is rated 4. A much stronger approach would be to multiply, permute, and multiply again. The permutation needs to move the weak low-order bytes into the high-order half of the block. Suitable permutations are 1. Reversing the order of the bytes, 2. Swapping the low-order and high-order halves of the block, or 3. Interleaving the low-order and high-order bytes in reverse order. If the bytes are numbered from high to low order using the hex digits 0 through F, then these 3 permutations can be represented by. If your programming language lets you manipulate the block as both 32-bit words and single bytes, it may be faster to reverse the order of the 4 words, resulting in this permutation. This cipher, designated MPM128, is rated 7. When you add substitution steps to this process, the strength shoots up. Let S1, S2, S3 and S4 be 4 independent, well-mixed keyed substitutions. Let P be the fixed permutation, 5BF, 4AE, 39D, 28C, 1706, and let M1, M2 and M3 be multiplication by 3 secret 128-bit integers. Then the cipher S1M1 PS2 M2 S3 PM3 S4, called Tiger, is rated 10. Section 15.8. Small integer multiplication. A miniature version of mult128 can be done using ordinary unsigned 32-bit multiplication. The 128-bit block is treated as 4 32-bit integers. Each of these integers is multiplied by a secret 32-bit integer modulo 2 to the power 32. The 4 multipliers must be odd to allow for deciphering later. This produces a 32-bit cipher. To get to a 128-bit cipher, the 4 separate 4-byte products can be treated as a 16-byte block and mixed using this fixed 16-key transposition, section 7.6. This transposition is followed by a second multiplication step, again treating the 16-byte block as 4 32-bit integers. You may use the same multipliers or new multipliers. This is followed by a second transposition and another round of multiplication, so that there are 3 rounds of multiplication and 2 rounds of transposition. This cipher is called Mult32 and is rated 7. It is much faster than any of the Mult128 cipher variants. Let's view the 16 bytes of a 128-bit block as a 4x4 matrix of bytes. The 4 bytes in any row of this matrix can be treated as a 32-bit integer. Normally, the 4 bytes of the integer are taken from left to right, with the leftmost byte being the high-order byte. However, they may also be taken in the opposite order, with the leftmost byte being the low-order byte. Consider the hexadecimal number 010200304. If we multiply this by the hexadecimal number 01010101 modulo 2 to the power 32 in the normal way, the result is hexadecimal 0A090704. If we multiply this in the reverse order, 040300201 by the hexadecimal number 01010101 modulo 2 to the power 32, the result is hexadecimal 0A060301. In a similar way, we can treat the 4 bytes in any column as a 32-bit integer, both in the top-to-bottom order and in the bottom-to-top order. Call the 2 horizontal directions east and west, and the 2 vertical directions north and south. If we multiply the rows and columns by odd 32-bit integers modulo 2 to the power 32 in the order east, north, west, south, this provides thorough mixing. This requires 16 separate 32-bit multipliers. The total key size is 16 times 31 equals 496 bits, not 16 times 32 equals 512, because the multipliers must be odd. This cipher, which could be called compass, is rated 8. To push the rating up to 10, add 1 or more rounds of substitution. For example, east, north, substitute, west, south. Better yet, add multiple substitutions like east substitute north, west substitute south. Call this compass S. Even if you use fixed substitutions, if they are highly nonlinear, compass S is rated 10. A different way to use small integer multiplication is to do cyclic multiplication. Let the bytes in each 32-bit row of the block be numbered 1, 2, 3, 4 from left to right, that is, from the high-order byte to the low-order byte. Multiply this by an odd integer modulo 2 to the power 32. Move byte 1 to the low-order end, so the order is now 2, 3, 4, 1. Multiply again by an odd integer modulo 2 to the power 32. Repeat this 2 or more times, so every byte occupies every position once. That is, the bytes are taken in order 1, 2, 3, 4, then 2, 3, 4, 1, 3, 4, 1, 2, and finally 4, 1, 2, 3. This should be done for each of the 4 rows of the 4x4 matrix of bytes, for a total of 16 multiplications and 12 cyclic shifts. Then the same operations are done on the columns. Altogether there are 32 multiplications and 24 cyclic shifts. This cyclic multiplication cipher is rated 8. It can have up to 32 different 32-bit multipliers for keys. The methods of this section can be combined with the methods of section 15.4 in a variety of ways. Here is just one example, which I will call MAT36. Take the message in blocks of 36 characters that are treated as 9 32-bit integers. These form a 3x3 matrix of integers modulo 2 to the power 32. This matrix will be multiplied by a secret 3x3 invertible matrix of integers. If you simply multiplied on the right by another 3x3 matrix, the low-order bytes of the 9 integers would be weakly enciphered. Instead, cycle the entire 36-byte block left by 16-bit positions, and then multiply the block on the right by a second secret 3x3 invertible matrix of integers. MAT36 is rated 8.